Okay. Welcome, everyone. Thanks for giving me the opportunity to speak on this very groundbreaking topic, quantum machine learning with TensorFlow Quantum. Um, and this is a brief background, my own background, and some of the things I've done in the past, and some of the things that currently I'm doing with quantum machine learning, quantum internet, some kind of quantum communication, and so forth in my startup Qulabs. Before I dive deep into quantum computing and how that relates to quantum machine learning, and TensorFlow and quantum TensorFlow, it's worthwhile to go back and revisit the history of classical electronic computing, which you see on the screen here. If you look at the top side, this is how the classical computing um, developed from 1906. It took 40 years to get to a ENIAC kind of a basic transistor-based computer. And then in 1950 was the first IC-based, integrated circuit-based computer was out. And if you follow along to 2016, 17, and now there are like billions of transistors sitting on a small chip. And you have this GPUs, TPUs, and a whole bunch of things, right? To contrast that with the 100-year that classical computing took to mature, if you look at the quantum computing cycle, it typically started from the computing aspect in 1981 with Richard Feynman. And when he suggested that if you want to simulate anything that's natural, then definitely it's very hard to do it through a classical computer. And we need, in fact, a classical system to perform the simulation. And that was one of the kickoff. And then subsequent decades with Shor and Grover, and a lot of research came in the next couple of decades to where we are now, where we have 50 to 70 qubits computing available on quantum. And today we have processor operating at 53 from Google with IBM. Google has 72 qubit, and there's a promise for 1,000 qubits by 2023. So that's the roadmap ahead. So in the next 20 to 25 minutes, let us explore what does all this mean and how to access this computing paradigm to solve some of the problems, which classical computing has kind of reached a point of saturation. We're going to even see examples of how quantum machine learning from utilizing frameworks like TensorFlow, Quantum, Penny Lane, and how that can be put together. So the next slide, which I have, is an overview of what quantum machine learning, I would say, has come up from the machine learning aspect of classical computing, and quantum computing aspects were brought together. And then currently we have frameworks like Cirq and TensorFlow, which kind of gives rise to TensorFlow Quantum from Google, which is what we are focusing on today to do the quantum machine learning kind of problems. So before that, I would want to just do a quick overview of what quantum computing is. And typically, it's a crossroads of quantum mechanics, quantum information theory, computer science, and some of the critical features like superposition, entanglement, are the ones that kind of drives this whole paradigm. And why quantum computing? As I said, it was because of Richard Feynman, and then a whole bunch of people like Benioff and Shor and Grover, all those various people kind of took us to the next level because of the saturation of Moore's law. And then, you have these inherently parallel kind of processing that you can do with quantum computing, and also having the ability to do entanglement and teleportation. So Some of these things are also used in secure communication. In case of your classical internet, there's always a possibility of someone like Eve to eavesdrop and capture your packets while it's being sent from Alice to Bob. But because of no clone theory postulate, it's pretty secure in quantum communication, which is currently being applied through something called quantum key distribution. So how is quantum computer different, right? So uh, if you look at this diagram, like the classical computing typically has a 0 and 1 as a bit, right? So there are two possibilities. It's very deterministic versus what you see on the quantum computer, the qubit, which is equivalent to your bit, has also a 0 and 1, but because of superposition, it is very probabilistic, and it could take any of the superpositioned state of, having alpha and beta as the amplitudes, which kind of would give you infinite positionings and infinite possibilities that you can run parallelly, right? So that's the motivation. And typically, if you look at if you can run, say, 300 bits, you can hardly capture an image, right? But with the 300 qubits, that's more number of possibilities than all the atoms in the universe. So it kind of gives you a motivation why it's desirable to use the parallelism and interference that quantum computing allows to solve really hard problem. Coming to now, I just wanted to just walk you through some basic, like qubit is a quantum bit, and then, it kind of differs from bit that it also takes on a continuous range of values, just like in the block sphere we saw in the previous diagram, where in case of classical, it can only have position which is north pole and south pole, versus quantum, it can be any vector on that sphere. So that's the infinitesimal kind of opportunity here. And some of these properties I talked about, the superposition state, and that kind of makes things probabilistic and continuous. So you have these amplitudes, alpha square and beta square, which should be total probability should be 1. And so exploiting the superposition, we can have parallel processing capacity. So some of the advantages of qubit-based or quantum-based computing, before we dive into the details, is parallelism. Then the space available for computation is 2 to the power n. System evolves in time according to unitary operation. So there is a possibility of defining chemical systems, a lot of natural systems which cannot be defined or simulated in natural in classical computing, can be very well studied, and possible solutions can be found. For example, in case of photosynthesis, nitrogenesis process, how do you come up with possible new enzyme, or in case of catalysis. So there are a whole bunch of places where this can be applied. Mathematically, there's something called Dirac rotations with a bracket. Means bracket, bra and ket comes from bracket. So typically a phase psi or a cat is given by alpha, alpha whatever, and 0 in this case, or beta 1. There are 2 states. So that's how it's represented. And amplitudes, which are alpha and beta, and the alpha square or the beta square is equal to 1 in the normalized state. So that's how it's represented, the qubit. And then equivalent to your classical registers, you have quantum registers. And classical register, for example, if it's a 3 bits, can have 000 to 111, 8 kind of states, versus quantum. But at any given point, classical can have only 1 state, whereas quantum can have all these 8 states that can be evaluated continuously and simultaneously. And we talked about entanglement, exclusive property of quantum. So multi-state superpositions. So controlled operations can be done simultaneously. There are things called gates, just like classical gates. We have unitary operators and gates, binary operators and gates, tertiary operators, which do certain operations, which makes computation possible. And then there are ways to uh, manipulate these gates to do calculations, logic gates. And there are various ways to do that through rotations, through different mathematical applying different techniques. So these are typical classical gates, your and, not, nor, NAND, all these general things which you're, I guess, familiar with. And their equivalent quantum gates are these. You have something called I, I gate, which is identity, which keeps the qubit in the same state. X gate, which is like a gate that rotates the qubit along x-axis, y-axis, z-axis. There are a whole bunch of other gates. Because of dearth of time, I don't think we can go in detail, but these are the various gates that are applied for doing the computations and eventually, you know, um, doing the logic in the algorithms. So these are some of the other gates. I'm just quickly going through that because of lack of time. But these are some of the gates: single qubit and 2 qubit gates for controlling and creating entanglement, and thereby applying these techniques for doing calculations. So this is a block sphere, as I earlier mentioned, along the z-axis, 0 and 1. That's what a classical kind of representation would be. But in case of quantum, it can be anywhere on the sphere, the state. So there's infinitesimal possibilities. There are different types of qubits through something called superconducting qubits, by polarization of the photons, spin qubits. Then there are quantum dots. There are these topological, which is being done by anions, which is what Microsoft is doing. Superconducting is Google and IBM. Ion trapped by IonQ and Honeywell. So there are different qubits being implemented. Most important thing to know in this whole aspect is the coherence, the amount of time the state that quantum qubit is in remains in that state before which you need to finish your computation, right? So that's the important concept to really understand. And I just put a generalized kind of a diagram to give you an idea of number of operations before errors occurs, number of gate speed for different type of like trapped ion versus superconducting versus silicon dots, so forth. Different type of where it stands in terms of number of gates and number of operations that can be done before the decoherence happens. So you want to be in the topmost right side, right? So this gives you some idea of some of these technologies that are available. So how do you do algorithms, and which would finally go to doing machine learning in quantum, is to uh, do through something called oracles or some functions, unitary. X and Y are 2 different qubits, and you apply some unitary and arrive at some results. So quantum algorithms, how do you design them, prepare the input registers, and you know come up with different techniques of these gates and do a measurement. So um, that's how the typical algorithm would look like this. You have a quantum state psi, and then that's with the input state, and then you do a bunch of single qubit operations, a multi-qubit operation. There is the whole, because of interference and entanglement, you'll be able to create some form of um, calculation where algorithm encodes answers in the final one of the output states of 2 to the power n would be your final results. And so that's how you arrive at. And these are some of the algorithms that currently, in terms of classical versus quantum, what kind of speed up you have, exponential versus polynomially speeding up, and some of the limitation that I've tried to capture here. So that's just an overview of quantum computing. The other aspect is the TensorFlow framework, which is already being used in classical, and how does that kind of uh, come together with other tools to provide you with ability to do quantum machine learning. So TensorFlow is typically a multi-dimensional array, right? So um, typically you have the concept of uh, uh, it is easy to build machine learning. People who have done classical machine learning enables researchers to build state-of-the-art machine learning models with Keras as a functional API, supports production everywhere, edge devices, and so forth. So that's the advantage of TensorFlow that we'll exploit. And it has a flexible architecture, CPU, GPU, TPU based, works on desktop servers, mobile device. It's very flexible. So now comes TensorFlow Quantum, which is a combination of TensorFlow and something called Circ, which is uh, another tool or another set of circuit simulating tool that IBM has come up with. So for those who are uninitiated in TensorFlow Quantum, it was launched I think earlier this year. And um, so what it does is like example that I could give is an existing TensorFlow estimator API that people use in the classical can essentially abstract many things like feed forward propagation or backward propagation for programmers, and hence they can kind of focus on writing the real code. And operations with Keras API is further abstracted to another level of making the writing application simple, right? So similarly, in case of TensorFlow Quantum, we can use the TensorFlow elements and Circ elements, which we'll see further in the like what we can do with standard TensorFlow Keras function like fit and compile. Like you have model.fit to fit a model or compile a model with model.compile, or we can kind of specify loss functions. There's the cost functions or loss functions and optimizers in case of model.compile. But however, it's not that simple, and because there's this whole notion of classical data and quantum data, and the quantum data, ingesting the quantum data is kind of a little bit of a challenge. So there are different type of quantum data that we can work with, and source of possible sources are many. You can see quantum machine learning has a different way through doing interference or doing inferences or doing, um, uh, as we said, entanglement, discovering new algorithms, particularly in the simulation of chemical systems or simulation of many bodies, quantum many body systems. So these are some of the ways the entanglement of these correlations kind of diverges exponentially, but it becomes very hard to simulate them at some point. But there are ways to generate these quantum data. And in case of our company, Qulabs, we are focusing on quantum communication and quantum internet, basically building the next gen internet, quantum internet, um, quantum repeaters, quantum receivers, and purifications. So when you have data and communication networks are noisy, and you have to distill these to improve quality. And some of these are being currently applied for through quantum machine learning. So some of the design principles for quantum for TensorFlow Quantum is so what there are four main things, right? Differentiability is important, just as in TensorFlow, in that we need to make sure that you can do forward and backward propagation calculations through differentiation. Also, you need to ensure that there is data that can be generated, and the circuit batching should allow parallel processing. And then execution backend agnostic, meaning you can switch between quantum simulator because of lack of availability of high-end hardware, currently quantum hardware. And there's a whole notion of having minimal disruption when you bridge between Circ and TensorFlow. Circ is we'll see very soon in the coming slides. We'll create the initial circuit, the algorithm, the gates, operations, and you feed into TensorFlow, which gives you TensorFlow quantum abilities to create the necessary algorithms, right? So, the next thing was to have a quick rundown on the stack, right? So this is a TensorFlow Quantum stack to do quantum machine learning, right? Um, if you note, it works ubiquitously with the lower part. You see TPU, GPU, CPU, and everything QPU. So uh, to put it simply, at the user interface, there are two sets of data, right? Data could be classical or quantum, and the TensorFlow Quantum supports both classical and quantum. I mean, classical data has to be converted to quantum before it can be used. But as I said, it's like either circuits or operators. That's what circ gives you, which is equivalent to gates, quantum gates, and you can map everything to tensors, and then use these standard TensorFlow layers, so that way TensorFlow Quantum has high-level layers that can be manipulated through matrix manipulation, and then you allow different kind of differentiations to do your backward propagation to create calculated gradients, and through the various operations that can be run through a simulator like Circ or on a hardware, quantum hardware, and something called QPU, quantum processing unit. And basically that's how the stack is utilized, right? So this is a typical layman, a very toy kind of a scenario of how a circuit workflow would be. If you look at the y-axis, you have 0, 1, 2, 3 qubits. Each of them are qubits, and AB, like horizontal lines, are kind of time. It's a progress in time where different gates and different operations are applied. And like ABC, what you see are different gates, and so that's kind of gives you a um, overview of how this flows. And Circ, the tool, you can be used to code these circuits, applying these gates. So um, that's how this would translate into something like a quantum algorithm, and which is what you run. We'll cover that in next few slides. The next slide. Oops. Okay. The next slide is a simple circuit. You see a simple circuit where two qubits are there, and you have these applying a X rotation along the X-axis with phase A, and Y with phase B. And there's a C0 gate, which is how you apply, like you give a Q0, Q1 as the two qubits, and you initiate them, and then you call a circuit, a method, which creates this whole connection between these different operations. And it's as simple as that. It's within 3 or 4 lines, you're able to create this algorithm with 2 qubits, and pass the circuit to the Circ simulator, and it'll execute what these rotation and these other C0 gate logic that has to be done. So we can see we can do machine learning on this finite space time that we have available, so that with the Circ. And below is the general kind of a circuit. Instead of saying 1 or 2 qubits, you apply n number of qubits, define a model through TensorFlow quantum layers, which I talked about earlier, give the data, and then let the model give the data to the model and create the model. So that's a way to run algorithm. This workflow kind of is very important. It builds the pipeline for running a typical algorithm, quantum machine algorithm. So you see a particular concrete suggestion to understand how this framework works, right? So here, looking at the hybrid, there's a discriminative kind of a hybrid model, typical to a machine learning kind of environment where interaction of different parts. So quantum, prepare quantum data set, and then you apply some parameters, evaluate the quantum model, then you do measurements, so you get classical data, and then you pump that data into your classical, some neural network, right? And then you evaluate the cost function, and then you give it back. So that this way you can optimize both the parameters for quantum circuit and classical circuit. So this is a good way to run a hybrid quantum machine learning kind of example. Um, so I think I think that gives me like few minutes, uh, so I have some of the applications that are currently people are working on in terms of chemistry, biology, in terms of physics, encryption, which is very big, communication. That's what something that we are working on. Different aspects of computing, especially the quantum machine learning aspects. So the various frameworks, like when I covered TensorFlow Quantum, there's something by Penny Lane, Xanadu, there's IBM Qiskit, whole bunch of different frameworks are continuously being created to enable people with the background for having done machine learning and TensorFlow kind of exposures, or having background in Python to be able to program in quantum machine learning. We're using some of these libraries. The summary of what we learned today, just a few minutes. So basic of quantum computing, motivation behind quantum using quantum computers, why hybrid quantum classical models work, why and how TensorFlow and Cirq together comes together to give us that TensorFlow Quantum, why use TensorFlow Quantum and Cirq, and then we saw how to build a hybrid classical quantum model for quantum machine learning. I think that's all I have for folks.